Hello everyone, and welcome to Recitation. Hopefully you enjoyed that little bit of fun I had with the intro. I'm sure I'll see some of your reactions in the next 30 to 40 seconds. But welcome back to this week's Recitation. I don't really have too much more to say. It's a relatively normal week, so let's go ahead and get started with my brand new document camera. So much nicer, much better quality image. Even goes a little lower. You can see the old shot markers back from when I was using the webcam, so I can go a little bit below that now. Plus, every time I barely touch this little TV table, it's not going to completely screw up the orientation of my camera. So basically, you guys are going to get some high quality education right now. Oh yeah, I'm seeing all your stuff. Oh, that's great. I had some fun. We'll see what I can keep doing for future weeks. But I had that idea for a while before I got that. That was what I spent this morning doing. Okay, so your normal recitation stuff. You've got a homework right now. That's homework 6. That's your HashMap homework. That's due this Friday on October 2nd. Normal deadline. Definitely, if you haven't started that by now, after this recitation, I recommend definitely starting it as soon as you can, because it is a bit of a harder homework. So don't wait until the last minute on it. You might regret that. However, in general, with homework 7 is kind of an exception. The homeworks tend to get a little easier from here. If you did really well on your BST homework, then homework 7 won't be that bad. So you'll be kind of in the clear in terms of homeworks in this class, at least, based on general feelings we get from students. Speaking of homework 7, that's your AVL homework. We've just started to talk about that in lecture. We'll get to it more next week in recitation especially. That's going to release on this Friday, but that's not going to be due until October 19th. So you get 2 weeks plus that extra weekend to work on it. Again, that's both because it's a bit of a longer homework and because it overlaps with a test week, so we don't want to overload you and have that stuff due on the same week. But also, just like what you had with homework 4 and exam 1, this is going to cause it to overlap with the next homework, so try not to get this done last minute, although usually homework 8 ends up being a 2-week homework anyway, just because it's long. So you'll get some more info about that next week, I'm sure. Speaking of exam 2, that is 2 weeks from tomorrow on the 14th. Next week I'll be sending out a topic list to you guys so you can see what's on it. I'll try to be very explicit on what is and isn't on the exam from that topic list, or sorry, what could and couldn't be on the exam. But just as a little bit of looking forward, coding is going to be through homework 6 potentially. We will have your homework 6 grades back to you before the exam. Homework 7 is obviously still ongoing at that point. Practice exam 2, I think the Canvas assignment has actually been there already, but I just went and published the actual file one under the practice exams folder. So that's there now. Again, it should be the exact same questions, just if you are already comfortable with the Canvas input and you just want to try the questions on your own or print it out or something, you can. Your recitation worksheet should already be on Canvas as per usual. Today we're going to talk a lot more about hash maps. We only barely covered an introduction into them last week. We're going to get much more in detail today and talk about the collision resolution strategies. We're also going to start talking about SkipLists a little bit. We're not going to get all the way through them, but we'll go most of the way. You don't have any kind of homework or anything on SkipLists. It's just kind of a little thing we talk about in this class. With that said, let's go ahead and get started. Hash maps, specifically, let's talk about adding as our first operation. Now I know I'm going to call it add a lot today, just because that's the terminology we've used a lot in this class with data structures, but this is usually the put method. So we have put some key and value. So I might say put at some points or add at other points. They're the exact same thing. On your homework it's called the put method. In Java it's called the put method, but sometimes it is we might call it add just for consistency with other data structures. Our basic procedure, if you remember from last week, is we take the hash of the key, remember, only the key, not the whole pair, just the key. Then we compress that hash to fit into the table. That whole process together looks something like this. We hash the key, mod it by the table length, and then take the absolute value, and that's how we get our index. And then with that calculated index, we add our key value pair there into our table. The issue comes up if that index in the table isn't empty. In this case, we have a collision, and then that's something we need to deal with one of our collision resolution strategies. We didn't talk about any of these last week, but we're going to talk about the 4 ones that we cover in this class today. Just to kind of reiterate what the index calculation looks like in your code, it's probably going to look something like this, where you just use key.hashcode. That's Java's default hashcode function. You should not try to write your own hashcode function for this assignment. Please don't. We've had students try to do it in the past. It goes really badly. So use Java's hashcode function, then mod by table.length, and then take the absolute value. You're allowed to use math.abs, that's in java.lang, it's perfectly acceptable. So this whole procedure in this specific order, and that's how you're going to get your index to calculate at. And this is what we sometimes might refer to as like the starting index, the index where the element is like most supposed to be at. You'll see later today we talk about some situations where we're looking at other indices, but this is always like our base index where we're starting at. We'll give you a few more seconds and then we'll start talking about our first collision resolution strategy. Alright, so let's get into strategy number 1, external chaining. So as a note, the one that you're doing on your homework, as a bit of a heads up, is the second one we're going to talk about, linear probing, just so you're aware and you don't try to do like some weird stuff on your homework, but any of these things are things that you could potentially see on an exam. So external chaining is our first strategy, and it's the one I'm covering first, probably because it's the most different from the rest of the ones we're going to talk about. We also sometimes call this closed addressing. The reason for that is that's because all of our map entries are going to end up exactly at that index they're supposed to, that index I had the calculation for on the previous page. Everything's going to end up exactly there, which is not the case for the other methods. How external chaining works is all of the entries in our table, instead of them just being ordinary single key value pairs, they're going to work as like linked lists of key value pairs. So an individual index, that's a really bad eye, an individual index can have multiple key value pairs all connected to each other in a linked list, and I'll show you some examples of what that looks like in a bit. But it's going to look something like this, where you have these indices, and each of these contain their own linked list, potentially. So it might have multiple things, it might have one thing, it might have 3 things, anything like that. Now I say that they function as linked lists. We're not going to like put entire like java.util.linked lists in there. Usually all we do is we take our map entry class and we just add a next variable onto the end of it, which references another map entry. That way it can kind of function as its own linked list, and each index of the table is the head. So we don't really keep track of like n different size variables or anything like that. It's a little bit simpler. Now, how do we add using external chaining? Well, like always, we're going to compute that index first. Then we're going to look at that index in the table, and we need to iterate through the entire linked list there. And why do we need to do that? Well, remember I mentioned last week that the keys in a hash map are all unique. It's not possible for us to have 2 entries in the hash map with the same key. That is wrong. We need to make sure that that never happens. So we have to iterate through the entire linked list in that index to check for duplicates. And again, that's only duplicate keys. We don't care about the value. Now, why do we only need to look through that specific linked list instead of the whole table? Well, because we chose the index to work at based on the hash of our key. If we're looking for a duplicate key, we can calculate the hash of that duplicate key. It's going to end up at the exact same spot. Remember that equal objects have equal hash codes. So then when you mod 2 equal hash codes, you obviously get the same thing. So we're going to end up, no matter how many times we do it, if we have a duplicate key, it's always going to end up at the same index. So we only need to look through the linked list at that specific index we've calculated. But we do need to look through the entire thing usually. If we look through that entire linked list and never find our duplicate key, then that means we're not adding a duplicate, and we can just add our new entry onto the very end of the linked list, or the beginning. It doesn't really make that big of a difference. Otherwise, if we do find a duplicate, then we just replace the value, and you usually return the old value that was in there. That's the procedure for what happens when you try to add a duplicate key into your hash map. So as I mentioned here, it doesn't normally matter whether you add to the front or back of these chains when you're doing your linear probing. It seems like it might be harder to add to the end of it because we don't keep track of like tail pointers or anything. But remember, you need to iterate through the entire list anyway to check for duplicates. So you always end up at the end of the linked list. So obviously you could add to the back really quickly, but you can always add to the front really quickly because it's a linked list and you have the head essentially. Normally it doesn't matter. It's going to matter when we're resizing our hash map. And resizing is the kind of a side thing I'm going to talk about next. So I'll give you a couple more seconds to take a picture or write this stuff down, and then we're going to talk about resizing for a little bit. All right. So we'll take a brief break from collision resolution just to talk about resizing, because it's important in hash maps. It's important in a lot of data, any array-based data structure, but hash maps especially. And we want to make sure we understand how it's going to work before we keep going on and potentially leave it in the dust. So with our other array data structures that we did, so array list, heaps, index, we waited until the array was completely full before we resized. With heaps, we obviously had that one empty spot in the beginning, but you get the point. Unlike that, with hash maps, we're not going to wait until the array is completely full. And you can obviously see why that might make sense for external chaining, because it might be possible that our array is never full. We might add like 20 things to a size 10 table, and it might happen that all 20 of those things end up in the exact same index, all in like one big linked list going down. And that's obviously not what we want in our hash map. We want things to kind of go to different indices, end up in different buckets, that sort of thing. So we're not going to wait until our hash map is full to resize. Instead, we're going to look at something called the load factor. Now, load factor is a simple calculation. We can just do the size of our hash map divided by the capacity. So remember, capacity is just table.length, and size is going to be the total number of key value pairs in the map. I'm going to need to, and writing the word pair today seems to be bad. I'm going to need to like add an extra word onto this later once we get to our other strategies. But for now, it seems obvious that it's the total number of key value pairs in the map. That's the size variable. So what we look at for load factor is if the new load factor, so after the add operation completed, so size plus 1 over capacity, if that number exceeds some maximum load factor that we set in advance, it's specific to our implementation. There's not like one load factor that works for everything. It tends to be somewhere in between like 0.5 and 0.75. I think it's 0.66 on your homework. I could be wrong about that. But if our new load factor after our add operation would exceed that, then we're going to resize the backing array of our hash map. An important detail of this is we check for this resize condition before we check for duplicates in our hash map. And that's just because checking for duplicates like this is potentially expensive because we might have to iterate through chains and stuff. So we just check for resize first because it's simple. And in the worst case, this might make us resize like one element earlier than we would normally want to, so it's really not that big of a deal to resize and then oops, it turned out we actually didn't need to add something. Well, now you've just got a bigger hash map. It's probably got smaller chains anyway, so you don't really lose out that much. An important detail with hash map resize is unlike the other methods, we can't just kind of copy our elements over to our new array. Now I said that with dex because you needed to do the kind of like unwrapping of stuff, but I really mean it with hash maps that there's no like blatant copy over we can do. We actually need to rehash and reinsert every element into our new table. Now that might seem weird because the hash value of them obviously doesn't change. The hash value of the key is never going to change at all if it's a correct hash function. But the compression function, that's the part that might change because now we're modding by a different table length. Obviously 20 mod 13 is going to be a different number than 20 mod 27 if those are our old and new table lengths. So we need to rehash and recompress every single element and reinsert it into the new table. Now, one nice thing is before we do our add operation, just while we're in the middle of this resize, there's no duplicates in our hash map anywhere because we're starting with a valid hash map, obviously. So we don't need to check for them, which in external chaining means that we can just add to the front of the chains without ever looking through it. So every element just goes at the front of whatever index it's supposed to be at in the new table. And it's really simple like that. You'll see with some of our other strategies, unfortunately, it's not quite so simple, but this is a big advantage we get with doing external chaining, is this lack of need to check for duplicates and that giving us some kind of efficiency advantage. Now I'll pause for a little bit just to give you some time to finish writing this down or ask some questions, because there haven't been too many questions so far, and I know that this can be a little weird, so I will give you a little bit to ask some questions if they popped up. Alright, not too much so far, so hopefully that means I'm doing a good job here. Again, huge shout out to my TAs for helping me out. This would not work without them. So let's get back to external chaining now that we understand kind of what resize looks like. And unfortunately, now that I've mentioned resize, I'm going to mostly ignore it for the rest of today, just because a lot of these examples are designed to work with these specific size tables, so I'm not going to be resizing in most of these examples today, even though it might kind of get some pretty high load factors. But it's important just to understand how resizing works. So one thing I didn't mention is I didn't mention how to remove, and that's mostly just because it's pretty straightforward. We compute the index that for our specific key, we iterate through that linked list to find whatever entry has the key we're looking for, and we remove it from the linked list just like any normal linked list remove. So with that said, let's go ahead and do some operations. This is going to be my little backing table, and these are the operations I'm going to perform. So we're just going to go ahead and do these in order. All of these operations, again, I have it as add here instead of put, same thing. It's the key first and then the value, and the important thing is I'm using integer keys here, so the hash of the key is just going to be the key itself. I'm not going to do any kind of fancy hash function. This is actually what Java does for normal integer keys, because it's really simple. So, when I add 1, 4, the hash of the key is 1. I do 1 mod the length of the table, so 1 mod 5, that's just 1. So I'm going to add the element right here at this index. So, next is 13, 8. So I look at 13. 13 is the hash of 13 is 13. I'm going to stop saying that at this point. Then we do 13 mod 5. That's going to give us 3, which means we go to index 3. There's no chain here, so there's nothing that we need to look through. We go ahead and add our item right there. Next up is 1, 13, and we can see before we start this operation that this is a duplicate key. So it's not going to be a really simple operation this time. We're actually going to need to look through some stuff and do some extra work. This time I'm actually going to redraw the table too, just so we can see the before and after. So pretend this doesn't exist for now. When we add 1, 13, we do 1 mod 5, and that tells us to look at index 1. We see there are elements in the chain here, so we start looking at them. This first one we look at, we compare the keys, and we see that they do have equal key. So what that means is I want to, this is an 8, sorry. The values aren't that important, but that is 13, 8. We see equal keys, which means we want to return this old value, the 4, and we're going to replace it with the new value that was passed in the 13. So it kind of functions like an update method. So now we have 1, 13 here. Next up, 21, 2. 21 mod 5 is going to be 1. So we go to index 1, I can rewrite the index numbers. We go to index 1, we see that there are elements there, so we look through them. 1 is not the same key as 21, so that's not a duplicate. And since that's everything in the chain, we can go ahead and add our new element onto the end. Here I'm clearly doing the end because it is much easier to do than rewriting everything just to add new elements in. So next operation, 0, 18. 0 mod 5 is 0, so we look at index 0. There's no chain here, so we can go ahead and add our new element. 0, 18. Then I'm gonna make a new table again because we're doing a remove. For this remove 21, remember 21 is the key. They only pass in the key to remove because they don't care about the value at that point. However, often that's what gets returned when you actually do this. But the person that's calling the remove operation doesn't care about the value. They don't need to know the value to perform the remove operation. That's the important part. So 21 mod 5 is 1. We see our elements here, so we're going to start looking through them. This first one, that's not the same key, so we keep going. Then we get to 21. That is the same key, so we're going to remove 21 from this hash map. And then we're left with exactly what you would expect. At index 1, now 113 is the only item in this chain, and that 21 too is just gone. Gone without a trace, nothing left. So, these are the results of our operations. I'll give people a few more seconds before we start moving on to our next collision resolution strategy. That's going to be linear probing, which is the one you're doing on your homework. And that one's a lot more involved than external chaining is. Something I want to mention, I meant to say it earlier when I was on the resize page, but I forgot. Your homework does include a specific resize backing table function, like a public method that you have to implement. That is because we want to test your resize separately, because resizing is a pretty important operation, and it is something that you can definitely mess up. So implement all your resize logic in that separate method, and then you should just call that method from your put method. And that's just for testing purposes. If you don't do that, if you write the logic twice or something, it's not the end of the world. You probably wouldn't lose points for it, unless they were wrong or you had some kind of mistake that was in one place but not the other. So just use that other method. That's going to make it a little bit easier to grade your stuff. But with that said, let's move on to our second strategy of the evening. Linear probing. I know I got a lot here, but we'll work through it. Linear probing is very different from external chaining. It's something that we might call open addressing, and that kind of applies to all of the remaining techniques that we're going to talk about. And that's because unlike external chaining, where our data was guaranteed to end up at the same index every time, with linear probing, it could potentially end up at different indices. So, what's our setup here? Our backing array, or our backing table, this time it's going to store individual map entries. So external chaining, we had these chains, these linked lists. That's kind of interchangeable, by the way, calling them chains or calling them linked lists. But with linear probing, we just have individual map entries, nothing special going on with that. What we are basically going to do, our basic process, is we compute the index that we're going to add at, then we try that index. We try to add at that specific index. If that doesn't work, if it's a collision, then we're going to try index plus 1. If that's a collision, we're going to try index plus 2, then index plus 3, etc., etc. Just going to keep going linearly, one spot at a time through the table. No fancy tricks or anything. If we find null, if we find any spot that has room in it, there's nothing else there, we can stop and we can add our new element in.
There's some other stopping conditions that we're going to talk about in a second. I just wanted to mention that here, that this stop when you find null isn't the only thing that's going to cause us to stop. Now, large-scale overview of remove. We are going to find the key we're trying to remove at. And when I say find the key, it's going to be the same strategy as above. We compute that index, we check that spot, then we check the next, then the next, etc. Then, once we find this key, we're going to mark it with a deleted flag. Sometimes we say like del, del when we're writing, because writing out the word deleted is apparently difficult. And that's what we're going to do. We're not going to set it to null. So with external chaining, we took it completely out of the hash map. With the linear probing, we're just going to set this deleted flag to true. Why do we do this? We'll see in a second, but the basic idea is it's possible that elements had to probe past the thing we're trying to remove, and if we set it to null, we're losing that knowledge that we used to probe past that spot. You'll see examples later where if we don't do this, it will cause a failure. So hold off for now. If you have questions about this, you'll see why we need this. Sometimes we call this deleted flag a tombstone marker. I usually just call it a deleted marker, but this is another thing you might see in like some course notes or something, or you might hear another TA call it a tombstone. So those are our basic overviews. Now let's start talking about the actual adding process, what it looks like in a little more detail. So in order to add a key value pair to our map, the first thing we do is compute the index. This should be kind of the expected thing for you. No matter what operation we're doing, if we're given a key, we should probably compute the corresponding index for that key first. Now this is going to be our starting index, I should specify. Because unlike external chaining, we might end up at a different index. So this is the index we start at. That's going to be your usual hash code mod absolute value. Then we're going to start looking at the table. So these steps are kind of all looking at whatever index we're currently on. If we look at an index and find that it's a deleted thing, so some kind of deleted flag, then if it's the first deleted index we've seen, so in this entire probing process, if we haven't seen any deleted markers up until now, we're going to save this index. We're going to remember it for later. That's going to be important. Another thing is if this deleted index has the same key we were trying to add, so if we encounter the same key but it's already deleted, then we're allowed to stop iterating immediately. And the reason for this is the reason we do this iteration in adding key value pairs is because we're trying to make sure we don't have a duplicate key. So if we encounter this duplicate key but it's already removed, we don't need to keep checking past it. It might take a little bit of work on your part to kind of convince yourself, but if you work through some examples, you'll see that if we encounter a deleted marker like this with the same key, it's not possible for us to have another non-deleted version of the same key later on. If there was going to be any other thing, we would have encountered it earlier, not later. So this kind of rule of thumb does work. Then, if it doesn't meet either of these conditions, if we see some deleted index that isn't our first deleted index and it's not the same key we're trying to look for, we can just ignore it and keep going forward. Our next case, if we see an index with a different key, again, all of these are non-deleted things because this condition handles any deleted thing we could have seen. If we see an index that has a different key and isn't deleted, we can just ignore it. We're only looking for duplicates here. Now I say ignore here, but we'll see we actually need to do one small thing later on. But we don't really need to care that much about what the different keys are. If we look at our index and we see something with the same key, so a non-removed same key, that's a duplicate case, then we can replace the value and return the old value. So this thing is like, if this condition happens, that's immediately the end of our method because it's going to return something. If we see null at some spot, then we can stop iterating. Now, I wrote stop iterating up here too. This applies there too. I just couldn't really write it twice. So I'll say stop iterating and this. So once we see null, we stop iterating, and we're going to place the key value pair at one of two places. If we've found a deleted index at some point in our iteration, so if this line ever happened, if we found a deleted marker and we saved the index, we're going to place our new key value pair there at that saved index. If we haven't found any deleted markers in our probing up to this point, we're just going to place it at this null marker that we found.
Now, why do we save these deleted indices? Well, they represent things that are no longer in our hash map. We only keep them around to make sure that we don't stop early when we do our probing, because if they were null, we would stop immediately upon seeing them. But there's no reason to specifically keep that deleted marker in the hash map. We just need something there. So if we're adding a new item and we find a deleted marker closer to where we started iterating than our null spot, we can just overwrite that deleted marker instead of adding it on to the end at the null spots. So this is how these deleted markers get overwritten. Then, after all of this, if we don't hit one of these stopping conditions, we're just going to increment our index by 1 and remod by the table.length, just to make sure we're in bounds so that we wrap back around if we go past the end of our table. And then this loop, kind of right here, is going to keep running over and over again. Some people like to write it instead of like incrementing by 1 at the end. They use a for loop where their variable keeps track of the number of iterations they do. So instead it ends up like index equals starting index plus h. Here h is the number of probes we've done. Starting underscore index. That mod table.length. That's another way to do it. And then you need to, I don't have room to write it here, but then you take the absolute value of that whole thing. That's another way to do it. Some people like this method, some people like this method. Really just a matter of personal preference. Oh, a great question about the deleted flag that I kind of want to say myself too. If you've looked at your map entry class for this homework 6, it just has an extra variable called isRemoved. So all you need to do is just for removing operations, you set that to true. To check if some element is removed, you just check if isRemoved is true or false. Something like that. So I'll give you a little bit to write this down, take a picture, digest this just to make sure you're understanding it, because there's a lot on this page and a lot of it's kind of important. And then we'll move on to a brief talk about remove and then some examples, because I'm sure that, or an example, because I'm sure that will help you a lot. Alright, so hopefully you guys have had some time to at least see this in your head. Some questions have been popping up. TAs have been helping answer them, but feel free to ask any questions you have. Remember, if you get like behind on something, you can always pause this live and just resume it. Pausing it isn't going to like put you behind a ton. You can always even just play it back at double speed until you get back up to the present. So don't worry about missing too much stuff if you have to pause. Alright. Now, let's keep going with linear probing. Removing is much simpler than adding, in the sense that we don't have to like be looking for duplicates, we're just looking for one specific key. All we do is we compute the index, we keep iterating until we find the desired key, and then we set the deleted flag to true. That's really all the process is for the remove method. One thing I do want to mention is before how I mentioned if we find an already removed key in the put method, we're allowed to stop earlier. Likewise, in the remove method, if we find the key we're looking for and it's already removed, we can throw our no such element exception because we know that that key in the map isn't there anymore. Because remember, removed keys are still there to us as the one implementing the map, but in terms of the user actually using the hash map, those keys and values are not in the map at all. One extra note I want to mention with linear probing And deleted flags is when we're doing our resize operation. You completely ignore the deleted elements. Those don't get copied over to the new table. Only the non-deleted elements, because we're doing all that reprobing again, so we don't need to keep track of where probing happened in the old table. So now let's do some examples. Hopefully that will help you a bit. The first thing we're going to add is this 2, 4. So 2 mod 5 is going to be 2. So we go to index 2 in our hash map. It's already null, so we can add 2, 4 right here. Then we can go to 12, 5. 12 mod 5 is 2, so we look at index 2. Index 2 is already occupied, so we just move over by 1 and look at the next spot. Index 3 is here, and it's unoccupied, so we can go ahead and add our 12, 5 here. Next up is 22, 8. 22 mod 5 is 2. Look at index 2, it's occupied. Look at index 3, it's occupied. Then we go to index 4, and that's empty. So we can go ahead and add 22, 8. Then here I'm gonna, after this point, go into a new table. Little diagonal, sorry about that. Now we're going to remove 12. So what we do is we... Sorry about that. 12 mod 5 is 2, so we look at index 2. That's not the key we're looking for. So we probe by 1. We get to index 3. That is the key we're looking for. So to remove it, all we need to do is set the deleted flag to true. So usually often in diagrammings, we would just replace this with like a big DEL in here instead of having the key in there. I'm going to keep the key in there just for reference because we remember that it can matter for our operations, but the important thing is that it's deleted. Now, I'm going to add 22, 9, and this is going to like simultaneously answer like 4 different questions that have popped up in chat. So I'm sorry, good job on asking the questions before the things became relevant, but this is going to explain a lot of things, both why we need the deleted marker and why we can't stop probing as soon as we find a deleted marker. So 22 mod the length of our table is 2, so we look at index 2. That is occupied, it's not a duplicate key, so we keep going, and we hit this deleted marker. Now, if we had nulled out this spot in the array instead of keeping a deleted marker, then we would have added 22, 9 here, and we would have had duplicate entries in our hash map, which is not, or duplicate keys in our hash map, which is not allowed. If we had added the element here as soon as we found a deleted marker to add at, then we would still have duplicate keys in the hash map, which is not allowed. So all we do is we remember this index. We remember I saw a deleted marker at index 3, and we continue probing. So we probe to index 4, we look and we see, oh hey, I have a duplicate key. So just like before, when we have a duplicate key, we're going to just replace the value, and we would return the old value back to our user. So this is our deleted marker. And now we have 22, 9 here. That value has been replaced. Next up is adding 32, 1. 32 mod 5 is 2. So we look at index 2, that's occupied. We look at index 3, it's occupied, but it's not occupied, it's a deleted marker. So we can't stop probing, but we remember this index for later. We keep going. Here, 22, 9, that's occupied. Then we could keep looking and see, okay, now we found a null spot. But now the question is, do we add this null spot we found at, or do we add this deleted marker we found here? Well, this deleted marker is a lot closer to where we were originally calculating our index to go. So we're going to use that deleted marker instead. And also, I just want to mention in advance, the procedure I just did slightly contradicts a efficiency optimization I'm going to show you later. I'm aware of that. I'm just explaining the basic process for now. So this deleted marker is going to get overridden by our 32, 1. And this is what we've got. Now to add 310, 3 mod 5 is index 3. We keep going, we probe by 1. Then we probe by 1 again, because this is occupied. We find this null spot here, and that's the spot we can add at. That's our example, so I'll give you some time to ask some more questions about that and look. A question we keep getting is, if we see a deleted entry with a matching key during put, do we still have to go to null, or can we just add there? So the answer is actually neither. It is correct that you don't have to keep probing and you don't have to go to null, but you don't necessarily add that index where you found the duplicate removed key. Just like what I mentioned previously, when we find, it's possible that we found a different non-duplicate removed entry earlier. So if we found that other removed flag closer to the spot where we started probing, that's where we're going to add instead. But it is true, once we see this duplicate deleted entry, so matching key but is deleted, we can stop probing. We shouldn't need to check any other indices, but that's not necessarily the index we're going to add at. We might add earlier. But great questions. This stuff is not straightforward. The deleted markers are weird, and this probing strategy is non-intuitive. So it's really good that you're asking so many questions about it. Alright, so now again I want to take a minor aside and talk about something that's mostly specific from your homework, and that is unfortunately going to slightly contradict what I just did in the example, but only slightly. And that is an extra thing we can do for the sake of efficiency. Remember how I said earlier that if we see a non-deleted key that doesn't have the same key that we're searching for, so it's not a duplicate, just some ordinary non-deleted element, instead of doing literally nothing, we can keep track of how many that we've iterated past. So we just have some kind of count variable, and every time we see a non-deleted key, we just increment it by 1. But when this count is exactly equal to size, this means that we've probed past every single element in our hash map, every single non-removed element in the hash map. That means everything past the elements we've seen, so starting from the index right afterwards, all the way back up to the position we originally started iterating from. All of those spots are either deleted markers or they're null spots. One of the two. We don't know which, but it can't be some non-deleted thing because we've seen all of them at this point. So what this means is during put, if we found a deleted spot already when we did this iterating, we can just add that deleted spot without probing any further. Or, if we somehow haven't found a deleted spot yet, that means the very next spot in the table has to either be a deleted spot or a null spot, and we can just add there instead. So that might be like starting index plus size mod table length, something like that. For stuff like remove and get, you can throw an exception because you've probed past all of the elements in your table and haven't found it. For contains key, you just return false. And then for stuff like the resize key set in values method, you just stop the method because you've already handled every single element. Now, a reason this is nice is because think about if you have a table that's all deleted markers. That's possible, that's a thing that can happen. If you have all deleted markers, then that method I showed on the other page, that probing technique, that would go through the table infinitely and never stop because it never finds that null spot it's looking for, and let's just say for the sake of argument that it never finds that deleted duplicate key that we're looking for. But in this case, with this efficiency added, we don't do any probing at all because we know our hash map is size 0, so there's no point in probing through the table because there's nothing in our hash map. We know that. That's information we have access to. So we can make these efficiencies. Now, just to show on my previous page where my contradiction was, here, when we were adding 32, we probed this element, found the deleted spot, then probed here.
after probing past this element, we've probed now the only two non-removed keys in our hash map, and we could instantly add that deleted marker. In my example, I said that we got to this null spot and saw that there was a null, but in your homework implementation, you wouldn't even check that null spot. You would instantly fill this deleted marker up because you passed two elements and the size of your hash map was 2. So I'll give you a little more time to think about this because this is an important thing. It seems like a really minor detail, but it can cause some big efficiency improvements, and it can remove some of the weird edge cases that come up if you don't keep track of this extra count. It does end up making the method a little bit messy because you have like now all these kind of an extra like if condition that's kind of wrapping everything, but it is overall for the better. All right, let's start talking about yes, you do need to do this extra efficiency thing. This is an important thing on your homework. Yeah, these probing loops are going to have a lot of if statements and loops involved in them. It's going to look kind of messy because there's a lot of different possibilities. But it's all for the sake of the really nice efficiencies that we're going to talk about later. Something on your homework is put is definitely the hardest method on your homework for homework 6. However, I recommend that you do homework 6. You do put method first on homework 6. And that sounds weird because it's the hardest one. Wouldn't you want to do some of the easier methods first and work your way up? The reason I recommend put first is because all of the other methods, remove, get, contains key, and resize, these ones are kind of separate, all of those are going to have really similar code to put, just kind of a subset of what you use. So if you code your put method first and it works correctly and you handle a bunch of like all the things that can pop up in that, then all you'll need to do for your other methods is basically copy paste your put code and delete things that don't apply to the other methods. And that's really all you need to do. So it's kind of a lot of work to get a put method working first, but if you do, you're almost done with your homework at that point. So that's my personal recommendation. You're obviously free to work on your homework in whatever order you wish. Let's talk about strategy number 3, quadratic probing. Now I have a lot less written for these, and that's just because A, it's not on your homework, and B, it's really similar to linear probing. This and the next strategy we're going to talk about both. So, it's similar to linear probing. We're going to calculate our index to look at. It's an open addressing method. Then we're going to check index, the spot we're trying to add at, index plus 1, the next spot right after it, but then instead of index plus 2, we're going to check index plus 4. And if that's still filled, then we're going to check index plus 9. And if that's still filled, we check index plus 16, index plus 25, etc., etc. The basic strategy, something I wrote down on the other thing too, is we take that original index, we add h squared, where h is the number of times we've probed so far, and then mod by our table length. So h would be 0, then 1, then 2, so on and so forth. So really similar to linear probing, just instead of checking the next spot and the spot right after, we do this extra method, so we're kind of jumping around the hash map a little more. And what this accomplishes is it spreads the data out a little bit better compared to linear probing. So linear probing, if we add like 5 things all like right next to each other, you get this big clump where everything kind of collides together, and as soon as you get one thing that goes past, then the things in the next spot all collide. With quadratic probing, these plus 4, plus 9, that can cause things to get put very far apart from each other, even though they might have been at similar indices or had a bunch of collisions together. And that can potentially help depending on what kind of data you're adding to your hash map. This can break up your data a little bit better. The one downside we can get is it's actually possible for quadratic probing to loop infinitely, which means no matter how many iterations you do, you always see the same non-removed indices. You never find any deleted markers, you never find any null spots. So what we do to account for this is after roughly n iterations of this probing, I say roughly n, sometimes it might be like n plus 1 or something, just so that we don't get like weird false flags. If we loop a bunch of times and don't encounter any spots to add at, we're just going to automatically resize our table.
because clearly if we're getting these big cases where we're getting potential infinite loops, clearly we should put some more room in our table so that this stops happening. That's one advantage of hash maps not needing to wait until they're full to resize, is we can just kind of resize just because we think our data is too grouped up and we're getting these issues. So that's one nice thing with quadratic probing. But overall, very similar to linear probing, so not going to spend too much time on it. It could show up on an exam, but it's not going to be on your homework or anything. Your homework is using linear probing. Alright. Our fourth and final technique of the evening is double hashing. Again, relatively similar to linear probing and quadratic probing, but instead of using like 1, 2, 3 or like 1 squared, 2 squared, 3 squared as an offset, we're going to use a second hash function. Then what the math is going to be is we take hash 1, this is the initial hash we calculate just by taking the hash code of our key. We add whatever hash 2 is, who knows, it's something, that multiplied by h, where h is the number of times we've probed, and then mod that thing by our table length. So to kind of summarize, linear probing added 1, then 2, then 3, then 4. Quadratic probing added 1 squared, then 2 squared, then 3 squared, then 4 squared. Double hashing added 1 times our second hash, 2 times our second hash, 3 times our second hash, 4 times our second hash. Now, what is the second hash function? Well, it can kind of be whatever it wants. It doesn't really matter that much. The very important thing is that our second hash function has to be some function that never returns 0. Now, to accomplish this, we can just take some function that could return 0 and just add 1 to it. And that's a possible option. But you can obviously see if this function did return 0 for some key, then this term over here would always be 0, and we would just check the same spot over and over again instead of actually probing anywhere. So what the specific function is doesn't matter very much, but it can't return 0. A really common example we use in this class is we do p minus our first hash mod p, so this is in parentheses I can specify, for just some prime number of p that's less than our table length. So 7 mod hash mod, or 7 minus hash mod 7, something like that. And you can see this is never going to be 0, because something mod p is always going to be between 0 and p minus 1 inclusive, which means p minus that is never going to be 0. Also, yeah, something I didn't mention, quadratic probing and double hashing, both of those use the deleted markers. External chaining is the only one we talk about that does not use deleted markers. So this is a common example of a second hash function, but there's not one hash function that you'd use for everything that works in general. This also spreads out the data a little bit better than linear probing. You can even see why it could potentially do better than quadratic probing, because even things that collide at the same initial index might go to a different second index because their second hash value might be different for all the different keys. However, this relies on us actually having a good second hash function that works for our specific table. So that's kind of the trade-off between double hashing and quadratic probing, is it relies on the second hash function too, so that needs to be good. Unfortunately, also like quadratic probing, this has the potential to infinitely loop, so we also might need to just do a resize after some number of probes if we'd never found a spot to add. A key note people always ask, if it was going to be on an exam, we would tell you exactly what the second hash function you're supposed to use is. You're never going to be expected to just come up with something out of thin air that works magically for your table. That would be impossible to grade. So we'll give you a second hash function if we want you to use it. But that's it for our different collision resolutions. Next we'll talk about efficiency and some common errors that people have on the homework, and then we'll do a brief introduction to skip lists. Alright. Efficiency is up next. So with efficiency, we split hash maps up into this kind of best and average case and the worst case. An important detail is what determines whether it's best, average, or worst. That's going to be dependent on the quality of our hash function.
if you remember, sometimes it gets talked about in 1331, our hash function is allowed to just be like return 0, return 5, return 7, something like that. That's a valid hash function, because if things are equal, well, they return the same hash. Everything returns the same hash. But that's very clearly a bad hash function, because it's going to make every single element collide at every single spot. So we don't want to do that, but it could happen, and that's where our worst case is going to come from. On average, when we don't have a lot of collisions, that means that when we calculate our index, that's either exactly going to be where our element is, or maybe we have to probe like once or twice. So all of these operations in the best and even in the average case are going to be O of 1. And that is awesome, because that is a super nice efficiency. That's pretty much the best efficiency we can have. So even though we might have to probe once or twice, on average it's still going to be roughly O of 1 compared to the amount of things we have in our table. So this is really nice, and this is why hash maps are super awesome. You remember I mentioned that they were the answer to a lot of interview questions? These are why, because these happen almost all the time. It's only in the worst case where we might have to look through every single element in our hash map because all of them collided, and something like that can be O of n. Now you guys probably know by now why I've left this add spot empty. That's because we're doing an add operation on an array. So something can be different here. But what I want to mention is that this worst case is only going to be different for linear probing and the other probing, so linear, quadratic, and double hashing. Someone mentioned why is it not asterisk for the best and average case for adding? Because in the average case, we don't have to resize. So resizing kind of gets wrapped up in the worst case, and this is where some weird semantics come up. We will try to be very specific about questions because of this. So I will say that linear probing, and when I write linear probing, I mean quadratic and double hashing too. Resize can be O of n squared. Now, why is this specified so strangely? Well, external chaining, remember I mentioned that cool efficiency thing that we could just add to the front of chains during a resize, which means that each individual element during a resize operation in external chaining is handled in constant time. We don't need to look through any chains no matter what. So even external chaining's resize case is O of n still, just the same as like the worst case if everything collided. But linear probing, if all of the elements collide in our new hash map, well then the first element that we're copying over goes in super easily. The second element collides one time and then goes in. Then the third element collides and then goes in. Then collides. So everything's going to collide together. So linear probing, if we have a really bad hash function, which again doesn't really happen in the real world at all, but it's still, we need to consider it from a theoretical perspective. If we have a really bad hash function, then our resize can be O of n squared. And that is kind of one weird case we need to handle. But again, these worst case stuff don't happen very often. So usually all of these operations are O of 1 with an O of n resize that can potentially come up. But this case does exist, and you might need to consider it. We will try to be specific on exam questions whether you should be considering amortized analysis or whether you should be considering the resize case for these operations. But that's an important thing to keep in mind. Now, some common errors that come up on people's homework. Remember, I mentioned this last week that we need to take the absolute value after we mod by the table length instead of before. Again, this is because we have this weird thing that the absolute value of negative 2 to the 31 in Java is equal to negative 2 to the 31. And that makes no sense because it's the absolute value of a negative number and it gives you a negative number back. And that's just because Java doesn't have an integer representation of positive 2 to the 31. So that's why you get this weird thing, and that's why we need to mod by our table length first. So make sure you have these in the right order or you will fail some tests. Another important thing is with the load factor check, remember that integer division kind of chops off the entire decimal place. So with load factor, we want to make sure we're working with doubles when we're doing our division. The easiest way to handle this is just do size plus 1.0 divided by table.length, We're already doing size +1 anyway, because we're checking if the next element overrides our load or overloads our table. But doing this 1.0, this causes this whole number to get cast to a double, and then a double divided by an int casts this up to a double, and that does double division, which gives you the decimal you want. If you left this 0.0 off, then you would get an int divided by an int. It's going to be like 0 point something, but that gets chopped down to 0, and 0 is always going to be less than your load factor, so you'll never resize. Another important detail for resizing is make sure that you're always modding by the new capacity, the capacity of your new table. That's an important detail. Don't mod by the old capacity, don't mod by like size or anything. Make sure you're modding by that new capacity or nothing's going to go in the right place. That's going to be it for HashMap stuff. We're going to talk a little bit about SkipLists, and then that will end our recitation off. All right. SkipLists are up next. These are everyone's favorite data structure. SkipLists are an example of a probability-based data structure. And what that means is that when we're adding our data, somewhere there is going to be randomness involved. That's what it means to have some kind of probability-based data structure. We're mostly just teaching SkipLists as an example of a randomized data structure, so if you kind of look more into data structures and stuff, when you see other examples of randomness, you kind of have some experience with working with random things, but they actually do have some practical uses in concurrent access situations, that things they do a little bit better than like BSTs. The basic structure of a SkipList is going to essentially work as a series of linked lists stacked on top of each other. So all linked lists each on their own level. And the basic idea is that every level of the SkipList is going to be some subset of the level beneath it. So the bottom level contains all of the data in the SkipList. The level right above the bottom level contains some of the data, not necessarily all. It could have all the data, it might not. Then the level above that contains some of or all of the level right below it, so on and so forth. The basic idea is going up the SkipList. If a piece of data disappears, it never suddenly reappears a bunch of levels above it. Now our nodes in a SkipList each have 4 pointers. They've got up, down, left, and right pointers, and I know I pointed to those wrong. Up, down, left, right. Up and down are pointers that are going to take us back and forth between our levels. So up will go to the level right above you, down will go to the level right beneath you. Left and right are going to work just like in a normal doubly linked list. Left takes us to kind of our previous thing, right takes us to kind of our next thing. So those are the ones you should be familiar with, but up and down are that's how we're going to get to between our levels. That's the new stuff. Now a little bit about the levels. Each level of the SkipList is stored in ascending order, which means the bottom level of our SkipList has all of the data in sorted order, but every level in and of itself does have sorted data in it. Each list starts with a phantom node that contains something representing negative infinity. How we implement that doesn't matter all that much. It can be like a node containing null or something, but it's going to represent negative infinity, and you'll see that on a diagram. Sometimes we end every list with positive infinity, but the positive infinities are not required. We need something for the negative infinities, not the positive ones. We also now need our entry point in the list. With linked lists, we entered in at the head. Trees, we entered in at the root. SkipLists, it's going to be that top left negative infinity node. That's where we're going to start all of our operations for SkipLists. Sometimes we might call that the head, but I'm going to try to keep calling it like the top left node or the entry point. Another note is we're usually going to cap the number of levels at roughly log n, just in case our luck is really bad. We don't want to potentially add a ton of extra levels in. You'll see that later. I do see a question that got asked. For the efficiency stuff for the homework, why do we need to keep track of the number of deleted keys? You don't. The only things you need to keep track of are the number of non-deleted keys, but that's called your size variable. The number of non-deleted keys that you've iterated over, which is the count that we use to keep track and make sure that we're not iterating after we've seen everything.
And once you encounter your first deleted key, you need to keep track of where it is, because that's the closest spot you're allowed to add at. All right, a couple more seconds on this, and then we'll take a look at what a skip list actually looks like and where the randomness comes in. So you guys can pause if you need some more time, but otherwise let's move on to our first operation. So where does the randomness come in with a skip list? Well, the idea is we're going to use coin flips to determine what's on every level above the bottom level. So the bottom level obviously has all of our data on it, but we're going to use coin flips to determine what goes on at the levels above that. What we're hoping for, and this we can't guarantee this because it's random, but what we're hoping for is that the bottom level has all of the n data. That's always a guarantee. Then the level above that has roughly n over 2 data. The level above that has roughly n over 4 data, so on and so forth. That's the hope with skip lists. And with how we implement them, that's going to be what we get on average, but obviously we can't guarantee that all the time. Now, how do we do search operations in a skip list? Let's say we have some skip list that looks like this. You see we have these negative infinities on the left. We've got this bottom level with all of our data, second level that has like some of the data, and the level above that with even less. I've kind of drawn these dash positive infinities here. Again, those you could have those there in your implementation. I believe they show up in the viz tool, but they're not necessary for a skip list to work. Now, how we do search is we start at the top left, negative infinity, and we look ahead to the right one node every time. If the next node is null or positive infinity, however we have it implemented, or it's greater than what we're looking for, we drop down a level. If we're at the bottom, we instantly stop because that means our data isn't in the skip lists. If the next node has the data we're looking for, well, then we're done. We found the data. But if the next node is less than the target, then we're going to move forward onto that next node. And if both of these cases, we're just going to repeat our process after that until we finally stop. So now let's search for, let's say, 35 in the skip list. So we start right here at the beginning, at this negative infinity. We look forward. 30 is less than 35, so we iterate to it. Then we look forward again. 50 is greater than 35, so we're going to drop down. Now we're here. We look forward again. In this case, 35 is exactly what we're looking for. So we go to it and we're done. That's the data we've searched for. So you'll notice when we made this first movement over here, we got to skip over all of the data that was down here. Turns out that was only one node, but that's not a big deal. You can imagine if we're looking for 50, then we get to skip over this data, and then we get to skip over all this data. So that's how these skip lists can be useful. Now let's say I'm looking for like 10. In this case, I start at negative infinity. 30 is greater than 10, so I drop down. I look again, 30 is still greater than 10, so I drop down. Then here, if I'm looking for 10, I've found it at this spot. So that would be what my search would look like if I was looking for 10. A couple more seconds, then we'll talk about adding, and that will wrap up our recitation. All right. Now, if you had that skip list already written down, it's the same one that we have right here. We're going to use it for our adding example too. So if you didn't get to completely write it down, it's just the same skip list again. How we do adds is the first step for some given element that we want to add is we're going to flip a coin until we get tails. And what we're going to do is the number of heads is the number of times we're going to promote the element. So if we flipped no heads and only tails, then it only goes on the bottom level. If we flip one heads, then it goes on one extra level above that, so on and so forth. Potentially, we might need to add new levels into our skip list if we flip too many heads, but we'd never want to add kind of a ton of extra levels if we get really unlucky coin flips.
Our basic procedure is we search the skip list to find the place where we're going to add. We're going to end up on the bottom level because we don't have duplicates in skip lists, so we're always going to end up on the bottom level after searching for our node. We're going to add our new element to the bottom level and then promote it one time per heads we flipped. So let's look at these three things we're going to add: 60, 20, and 25. Usually with skip list operations, you're given just a string of coin flips. Sometimes more the coin flips than you actually need. You'll see here I have too many coin flips, and then you kind of group them up per add. So I've grouped the first 3 heads and the tails for the 60, the next head tails for the 20, and the tails for the 25. So you stop after every set of tails, or after every tails. So let's go and add 60. So we start at negative infinity. 30 is less than 60, so we move over. 50 is less than 60, so we move over, so we got to skip all this data. Then this null over here, I don't even have the infinities written, but this null, that indicates we drop down. Then we drop down again. Then here we're on the bottom level, so this indicates that this is the spot to add 60, immediately to the right of this node. So we add 60 on the bottom level, and then we have 3 heads, so we promote 3 times. So promote once, promote twice, and then now to promote again, we need to add a new level to our skip list. So that means we add that new negative infinity in, and we add this new 60 in up here. So we've added it in and promoted it 3 times. Now, let's look at adding 20. Again, we start at negative infinity. 60 is greater than 20, so we drop down. 30 is greater than 20, so we drop down. 30 is greater than 20, we drop down. 10 is less than 20, so we move over. 30 is greater than 20, so we would try to drop down, but we're on the bottom level, which means this is the spot to add our node, right here. And we got 1 heads, which means we promote it 1 time. So now 20 is up here too. Next we'd add 25. 60 is greater than 25. 30 is greater than 25. 20 is less than 25, so we hop over. 30 is greater, so we drop down. 30 is greater, we're on the bottom level. So we add our new 25 element right here. And we don't have any heads for this coin flip, so we don't do any promotion at all. So that is skip list adding. Next week we're going to talk about removing, and we're going to talk about efficiencies. Hopefully this was mostly understandable for you guys. Probably have enough time to fit in our weekly card trick without going over by too much. So I will feel free to keep asking your questions if you still have some about skip lists. We'll talk more about them next week though, and you don't have to like code them or anything. But TAs can keep answering your questions. And I think we're going to try to quickly do our weekly card trick. Alright. Grab this week's deck. It is my Theory 11 Citizens deck. Super fun. Always like to show off on these. The basic trick I'm going to be doing is I'm going to be using cutting the deck in order to find some kind of 4 of a kind in the deck. But instead of doing it normally, how I'm going to do it is I'm going to do it with face up cards shuffled into face down cards. Shuffle those together a little bit. So now we're going to have like face up and face down cards in this. And I'm going to have to find the 4 of a kind in this mess. So first, I'm going to have to obviously find the first things we're looking for. So I'm going to need to actually choose what 4 of a kind. So just going to be doing cuts over and over again. And let's do 8s. 8s seem like a pretty good 4 of a kind to find. So I'm going to set all of the cards down after we find them, so you can keep track of how many we found so far. So now we have to look for the second 8. You can actually kind of think of this kind of like probing in a hash map, is I'm just checking like spots after another. I know where the elements are going to be in this deck, so I know exactly how much I need to probe to find the next 8 that we're looking for. Now that I've found this next 8, we can go ahead and set it down. Sorry about that. Alright, third 8, going to be a little bit harder to find. I might have to probe a couple more times. Go ahead and look once, look twice. I think this one's going to be 4 to find, so it should be right about here. Yep, I've went ahead and found the next 8, so I can set that down.
Last one's always the hardest to find, so hopefully it works out okay. Here, here. Actually, if I'm correct, it should be right about here. No, that's a queen. So that didn't go so hot, but maybe I can get this queen to somehow turn into an 8. That would be pretty cool, right? So I can try to like absorb the 8 energy from all these 3 cards, apply some magic to this, and no, it's still a queen. That would have been cool though to turn it into an 8. But what I did instead while you weren't watching was I took these 3 8s and I instead turned these 3 8s into queens. So that was pretty cool. You probably weren't prepared for that. But another thing is you may wonder what happened to the 8s if suddenly these are all queens. Well, if we look through the deck, suddenly somehow in all of that mess, now the deck is completely fixed and everything is face down, except for the 4 8s that we were looking for earlier. And that's the trick of the week. I only went about a minute over. Thank you guys for showing up. I'm just going to hold on here for a little bit, let the stream catch up, and then go ahead and end it off. So thank you guys for coming in tonight.